Hey all dear students, this is Prajesh Chaudhary, your Quantum Guru. In this video, I am going to discuss a very beautiful problem of electrodynamics, simple yet conceptual, from 200 more puzzling physics problems. So here is the question. So the question states, a chocolate figure of Santa Claus wrapped in aluminum foil is electrically charged and hangs on a insulating cord. The figure slowly loses its charge because the air has a small but non-zero conductivity sigma. Assuming that the air's conductivity is everywhere the same, how long will it take for the Santa's charge to half? So basically Santa is getting electrically discharged. So we have to find at what time from the initial value the charge of the Santa Claus will become half, basically the half-life of the discharging. So what we want to think of, just think that hypothetically make a convex surface at which the Santa Claus figure is there. So suppose enclose the figure of Santa Claus within a closed convex surface. So now suppose assume that this is a closed convex surface, and in that figure, in that surface, Santa Claus is there. And there is a charge here. So what we want to take that, we want to take a very small little element, and this element I have taken on that surface. That surface area is dA vector, infinitesimally small. So before I go for the Gauss law, just try to understand that the surface is a charge, so it has electric field. And like suppose if a charge is going in a naked wire and I'm here and I'm not getting electrocuted. Why? Because the charge from the wire is not coming to me. But what happens if the charge going through the wire comes through air to me? And that happens when the air gets dielectrically, there is a dielectric background of the air. If the charge is very large, so what it can do, its electric field can break down the dielectric. The electric field would be so large that the air molecules, which are essentially dielectric, can get polarized. So the air molecule will be split into positive and negative charge, and through them the charge can come to me, so I will get electrocuted. So same here can happen if this charge is very large, and charge is very large, so there is a very large electric field around that, and that electric field can dissociate or break down the dielectric molecules of the air, and air has a conductivity, so through them the charge can go. So the charge will go from the Santa Claus figure to air. So suppose at this location where I have taken this element, the area vector is dA, the sigma for the air here also is sigma, that is same everywhere, electric field is E, and the current density is J. So from the Ohm's law in the vector form, we know that the J is equal to sigma E. So J vector and E vector are in parallel, and this is the area vector. So the rate of the current flowing through the surface, if the charges are flowing out of the surface, so the charge at the Santa Claus surface would decrease. So the current is the minus dq by dt. Current is the minus dq by dt. And we also know that current is the flux of current density. Electric current is the flux of current density. So this whole figure, the current crossing through this whole figure is the flux of the current density, and that would be integral J dot dA on the surface S, and put J is equal to sigma E here, and sigma is constant, we can take outside sigma, so that would be simply sigma integral E dot dA. And what is integral E dot dA on S? Obviously that is a total flux crossing through that Santa Claus surface. So and that flux is the this would be variable thing, and that is at time t, so that flux would be total charge within that surface divided by epsilon naught. So at this time the charge is qt, so that is a sigma q by epsilon naught. So now we have a differential equation dq by dt is equal to minus sigma q by epsilon naught. So dq by dt, so I will take a similar term on one side, so dq by q is equal to minus sigma by epsilon naught dt. That is a very simple linear equation, one dimensional differential equation, and like we solved the case of the discharging of a capacitor, similar equation is that. So integrate it with suitable limit, and before that we can simplify that thing. We can take this epsilon naught by sigma as a tau, and this has a dimension of obviously time, and that is called time constant. So this equation will reduce to dt by minus dt by tau, and integrate it on both sides, dq by q minus dt by tau. At initial moment the charge was say q naught, and at time t the charge has become q. So integrated, and we'll get this integration as a q is equal to q naught e power minus t by tau. This tau here is a mean time, and half-life time is the mean time times ln2, or simply the time at which the charge will reduce to the initial values half. So put q is equal to q naught by 2, you will get t is equal to tau ln2, and that's what we are asked to. Thank you.